Hello and welcome to this presentation related to heat energy, usually given symbol Q. The formula we'll be using to calculate heat energy is Q is equal to mc delta T. M is the mass, C is the specific heat capacity, and delta T is the change in temperature, delta T being defined as final temperature of a body minus the initial temperature of a body. We will also be referring to various temperature scales, the commonly used Celsius scale, degrees C, and also the SI base unit of temperature, the Kelvin. Here's a brief presentation overview. We commence with some definitions. We define heat energy, symbol capital Q, and specific heat capacity, shortened to SHC, and denoted as symbol lowercase c. We state the heat energy equation, that's Q is equal to mc delta T. We overview the temperature scales referred to, that's the Celsius degree C scale and the Kelvin, the absolute temperature scale. We state typical SHC values for various substances. Then we have a series of examples. Example 1 converts what's termed specific heat to specific heat capacity. You'll see within the presentation that specific heat is defined as the specific heat capacity of a particular substance divided by the specific heat capacity of water. Example 2 calculates the heat energy required to raise the temperature of a particular body. Example 3 calculates the initial temperature, T suffix I, given various stated parameters within the problem. Just note there is some transposition of the heat energy equation required within example 3. Then there are 4 exercises for you to undertake at your own pace, although the full work solutions are included. And finally, the presentation concludes with some questions for you to attempt in your own time. For your reference, here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation. But please note, these times are rounded to the nearest minute. Some definitions. So heat or heat energy, symbol Q, is defined as the transfer of energy occurring between two systems or two bodies when there is a temperature difference between them. Note that heat is a scalar quantity, so it has a magnitude but no direction, and it's measured using the SI unit of the joule, capital J. Just notice as a reference, as with work or mechanical energy, these again are scalar quantities. They have no direction, but they can be positive or negative. So in this case, positive heat energy is energy into the system or into the body, and negative heat energy is heat energy extracted from the system or the body. Specific heat capacity, usually given the symbol C, is defined as the amount of heat energy that transfers into or out of 1 kilogram of material when the temperature changes by 1 degree C or 1 K. SHC has the SI unit of the joule per kilogram per K, or joule per kilogram per degree C. Notice these can also be written in terms of the negative index, so joule kilogram negative 1, K negative 1, or joule kilogram negative 1, degree C negative 1. I will interchange the way the unit can be stated throughout the presentation, so you become accustomed to see the various forms. Let's consider the calculation of heat energy, symbol capital Q. So for a mass, M, subject to a change in temperature, delta T, from initial temperature Ti to final temperature Tf, the heat transfer is given by the equation Q is equal to M multiplied by C multiplied by delta T. where M is the mass having the unit of the kilogram, C is the specific heat capacity having the unit of the joule per kilogram per K or joule per kilogram per degree C, and delta T is calculated from the formula of the final temperature Tf minus the initial temperature Ti. And delta T can be calculated using both Tf and Ti in Kelvin or Tf and Ti in degrees C. For reference, I've added some conversions here. These may occur in some of the questions we review later. And that's 1 litre is equivalent to 1 kilogram, and 1 ton is equivalent to 1,000 kilograms. Let's recap temperature scales. We've reviewed these in previous presentations. Essentially, there are 2 temperature scales in common use. The most common is the Celsius degree C scale, and the second one refers to the SI base unit of temperature, generally used for scientific work, and that's the Kelvin, symbol capital K, often referred to as the absolute scale. On the right hand side of the slide we have a sketch showing the Celsius scale on the right and the Kelvin scale on the left. This illustration relates to water. We know water freezes at 0 degrees C and water boils at 100 degrees C. In terms of the Kelvin scale, water freezes at 273 K and water boils at 373 K. So what we notice straight away is that the increments of the Kelvin scale and the Celsius scale are the same. There's 100 degrees C between water freezing and boiling, and we can see there's 100 K between the water freezing and the water boiling on the Kelvin scale. And that's very useful to know with regards to the calculations we're going to perform in this particular presentation. So 1 degree C temperature rise is equivalent to 1 K temperature rise. So for the same system or body we're considering, 1 joule per kilogram per degree C will be equivalent to 1 joule per kilogram per K. As shown in figure 1, we've illustrated this using the freezing and boiling points of water. Figure 1. Now, as we already know from previous work, the temperature of a substance is no indication as to the amount of heat or heat energy it contains. Temperature is merely a measure of the hotness level. And just note for conversions, to convert from degree C to Kelvin K, we add 273 to our degree C temperature. So 80 degrees C converted to Kelvin, we add 273 to determine the Kelvin value. And if we want to convert Kelvin K into Celsius degrees C, we now subtract 273 from the Kelvin value. So 80 K minus 273 produces a value in degrees C. And again, you can see this from figure 1. Kelvin relates to the absolute scale. So 0 Kelvin is considered to be when a body has no molecular movement. And on the Celsius scale, that would be negative 273 degrees, or often referred to as minus 273 degrees C. Just note I'm using integer values here for my temperatures in figure 1. I'm ignoring any decimal places here. And that's sufficiently accurate for the work we're going to undertake in this presentation. Let's consider typical values of specific heat capacity. So the table on the next slide will show us typical values of specific heat capacity, SHC for short, for various substances. You'll see in a moment from the table 1 kilogram of water requires 4,186 joules of heat energy to raise its temperature through 1 degree Celsius, 1 degree C. Thus the specific heat capacity, symbol lowercase c, of water is 4,186 joules per kilogram per 1 degree Celsius. So this value is usually written as 4,186 joules per kilogram per degree C, or of course we know can be written as joules per kilogram per K. Just note for reference, For solids, the specific heat capacity is assumed constant, doesn't vary with temperature. However, the specific heat capacity of liquids and gases show a slight variation with pressure and a large variation with temperature. So here's table 1 from our notes showing typical values of specific heat capacity, C. These are purely typical values. If you undertake your own research or use your own reference sources, you'll probably find slightly different values for particular materials shown here, and that's often because of the chemical composition and the various alloying elements that are used within the materials. So assume these are typical values. Left-hand column, here we have the particular substance, a range of liquid, gases and solids. In the center column we have the specific heat capacity, read in terms of joules per kilogram per degree C or joule per kilogram per K. And now on the right hand column I have specific heat. Now specific heat is relative to water. It's very much like a relative density that we've used in previous presentations when we're considering fluid mechanics. To calculate the specific heat, we will consider the specific heat capacity of a particular substance. For air, that's 1000 joules per kilogram per K. And then we divide the 1000 by the specific heat capacity of water, which we know is 4186. That calculates to a specific heat value of 0.239. Note there's no unit for specific heat. So be careful with some of the questions we're going to consider within this presentation. Often the specific heat capacity is given in the question or can be extracted from this table, but occasionally we may be given specific heat values, so we need to understand how to convert them into specific heat capacities. So here's the full listing of table 1. You'll note now that for water, having a specific heat capacity of 4186 joules per kilogram per K, then the specific heat is obviously a value of 1. Let's consider a few tutorial examples. Example 1, we've got to determine the specific heat capacity of gold, given the specific heat value of gold is 0.031. Here's our solution. So given the specific heat of gold, 0.031, we need to know the specific heat capacity of water, denoted that as C suffix W here, and that's extracted from our table 1, shown here, written in terms of joules per kilogram K here. So the specific heat capacity of gold, C suffix G, is simply the specific heat value multiplied by the specific heat capacity of water. So that evaluates to 130 joules per kilogram per K. Example 2, we're asked to determine the quantity of heat energy, that will be symbol Q, to raise the temperature of 20 kilograms of aluminium alloy from 100 degrees C to 150 degrees C. It's suggested to refer to table 1 for appropriate values. In other words, to find the specific heat capacity in this case. So from the question, the mass of the aluminium alloy M, 20 kilograms. From table 1, the specific heat capacity for aluminium alloy C is 904 joules per kilogram per K. Here's our table 1 extract. For aluminium, the specific heat capacity here, 904 joules per kilogram per K. And the temperature rise in this particular case of the aluminium alloy mass, labelled delta T, is the final temperature minus the initial temperature. So that's 150 degrees minus 100 degrees. So 50 degrees C, or of course that could be 50 K, is the temperature rise for example 2. So to calculate the heat energy required, Q is simply M multiplied by C multiplied by delta T. Inserting the values to find Q, heat energy required to raise the temperature of the aluminium alloy in this case is 904 times 10 to the 3 joules, or of course that's 904 kilojoules. Example 3, the quantity of heat energy absorbed by 750 grams of a brass machining was found to be 20 kilojoules. We've got to calculate the initial temperature, the brass, if its final temperature was 125 degrees C. Again, we refer to table 1 for the value of specific heat capacity. So from the question, the mass of the brass is actually stated as 750 grams. So I've converted that straight away into kilograms, 0.75 kilograms. The quantity of heat energy input, absorbed, Q, is 20 kilojoules, so that's 20 times 10 to the 3 joules. And the specific heat capacity of brass is extracted from table 1. So table 1, substance is brass. We can see the specific heat capacity is 385 joules per kilogram per K, and that's written here. We're informed the final temperature of the brass machine in TF is 125 degrees C. So this solution will involve some transposition. We know that heat energy required, Q, is M multiplied by C of the brass, multiplied by delta T, where delta T is TF minus TI. So rearranging for delta T, that's simply Q divided by M divided by C. Inserting the values from above, the change in temperature is 69.3 degrees, and from delta T is equal to TF minus TI. If we add TI to both sides of the equation and subtract delta T from both sides of the equation, then the initial temperature, TI, is TF minus delta T. The final temperature was 125 degrees C. We just calculated the change in temperature above. So the initial temperature is approximately 56 degrees C. Here's some exercises. Exercise 1. We're asked to determine the quantity of heat energy required to raise the temperature of 5 kilograms of steel from 20 degrees C to 800 degrees C. We're given in the question the specific heat capacity of steel. It's 494 joules per kilogram per degree C. Answer is shown in the bracket here. I would encourage you to stop the presentation and attempt exercise 1, but the full work solution is shown on the following slide. So exercise 1 is the solution. I'm going to let you review these solutions at your own pace. Just note when calculating the temperature rise, delta T, is always the final temperature, as given in the question, minus the initial temperature, given in the question, to calculate the change in temperature. The final value of heat energy Q was stated in megajoules. Exercise 2. The quantity of heat energy absorbed by 2 kilograms of copper was found to be 100 kilojoules. We've got to determine the final temperature of the copper if it was initially at 10 degrees C. We refer to table 1 for the appropriate C value. Again, I'd encourage you to stop the presentation and attempt exercise 2, but the full solution's on the following slide. Exercise 2, full solution here. Again, I'll let you review the solution at your own pace. Notice the SHC for copper is 394 joules per kilogram per K, and that was extracted from table 1, copper value shown here. So a similar approach to the solution of example 3. From the heat energy equation, we transpose for delta T, we find the change in temperature, but this time we're asked to calculate the final temperature, so TF. So to transpose the delta T equation, we simply add Ti to both sides of the equation. So TF is equal to delta T, add Ti. Answer is approximately 137 degrees C. Exercise 3. A steel component is quenched, that's cooled very rapidly, in a tank of water. The component has a mass of 1.7 kilograms. Its initial temperature is 850 degrees C. We've got to determine the quantity of heat energy that's given up to the water if the final temperature of the component is 25 degrees C. Specific heat capacity for steel is given in the question. Answer for the heat energy given up by the steel as it cools in the water given in the bracket. Again, I'd encourage you to stop the presentation and attempt exercise 3, but the full solution is shown on the following slide. Exercise 3, full solution. Again, I'll let you review this at your own pace, but just notice here when calculating the change in temperature, delta T, the formula is always TF, which in this case is 25 degrees, minus TI, in this case that's 850 degrees. So we have a negative change in temperature, because of course the steel component is being cooled in a tank of water. So when we calculate the value of Q, because we're using the negative delta T, the value of Q will actually be a negative value. And that essentially means heat energy lost or given up by the steel. So notice the answer stated in the original question was positive, because the question asks for the heat energy given up by the water, which is in this case a positive value. But in the actual arithmetic, Q calculated to be a negative value, indicating its heat energy out of the system or out of the body. So a subtle consideration to be aware of. Exercise 4. If an industrial oven can supply a maximum of 1 gigajoule of energy and has a maximum temperature range of 450 degrees C, we've got to calculate the mass of the largest steel component that can be accommodated within this specification. Again, we refer to Table 1 for the specific heat capacity of steel. The answer is shown in the bracket here. Again, I would encourage you to start the presentation and attempt exercise 4, but the full solution is shown on the following slide. Exercise 4, full solution. So in this exercise, we have to find the maximum mass of a component that can be placed in the oven, given the specification. We're given the heat input, Q, is 1 gigajoule, that's 10 to the 9 joules. And the specific heat capacity, C, we obtained from Table 1. So here's Table 1 for steel. Here's our specific heat capacity. So 494 joules per kilogram per K. And the maximum temperature range we're given for this particular oven, delta T, is 450 degrees C. So again, transposition required from our heat formula. Q is equal to MC delta T. We rearrange for M by dividing both sides by C and delta T and inserting the values. The maximum mass we can use is 4,498 kilograms, so the mass is approximately 5 tons. If you work through all the examples and the various exercises contained within this presentation, you should be able to have a good attempt at these questions. I'll let you read them at your own pace. Question 1H, 2H and 3H. Answers to all questions are shown in the brackets. Question 4H and question 5H. Just note in question 4H, the specific heat of a forging is given. So remember from the initial part of the presentation how to convert specific heat into specific heat capacity. Answers to the questions are shown in the brackets. In question 6H, 7H and 8H. Just notice in question 8H, we're given the dimensions of a workshop here, and we're given the mass density of air. Then to determine the actual mass of the air to be changed, we will need to use the equation for density. Density is equal to mass divided by volume. So by transposing this equation, we can find the mass that has to be changed every 2 hours. It's actually a very standard calculation here, but we do need to initially calculate that volume. I'll let you think through the problem at your own pace here. A nice little practical question to engage with, as this is a typical problem that can occur in industry where we have to undertake room changes per hour, whether it's in a workshop, maybe due to the use of certain chemicals that are being used, whether it's in a laboratory, whether it's in an aircraft, for example. This kind of problem does occur. Answers to all questions are shown in the brackets. So question 9H, first part of the question is quite standard for us. Just note we're given the specific heat of the shaft material. We have to calculate the quantity of heat energy required to undertake the hardening process. Be careful, in part 2, we now have to find the heat energy required to the furnace in order to supply the heat energy to the 10 shafts. But the furnace efficiency is only 25%. So you need to make use of the equation shown here. Efficiency eta is equal to the heat output from the furnace. That's the heat energy required in part 1. So what's the heat energy required to the furnace? So a little bit of transposition of the equation here to calculate the heat energy required to the furnace, assuming it's only 25% efficient. I'll let you think through the problem for yourself. The answers are shown in the bracket here. And question 10H, again, read the question carefully. You'll notice in the question you are given a volumetric flow rate effectively here per minute related to the cooling water circulated in the radiator. I suggest you convert that into kilograms per second to give you a mass flow rate, and then treat the mass flow rate as your M value in your calculations. You're basically working out the power required because it's the quantity of heat passed to the cooling water per second. So that's joules per second, which of course is the watt. So I've given the answer here in terms of kilojoules per second, but you could state that in terms of watts if you prefer. Again, I'll let you think through question 10H for yourself. There is a note in the question for your reference. Finally, question 11H. Again, I'll let you read it at your own pace. Just notice from the question you're given mechanical energy converted to heat energy per minute. So in this case, you actually have the energy in terms of joules per minute. So consider that as your Q value. And then using the Q is equal to MC delta T value, rearranged for M. But you can evaluate your M in terms of kilograms per minute, or, as the answer states here, litres per minute. And for your reference, here's the bibliography used to help generate this presentation, which I hope has been of interest to you. And thank you for viewing.